is equal to Pn. Okay? So I said that. So this is essentially what I'm going to work with. And we explain what we were doing, what is the random sequence. And we're saying the following, that when we have the integers, 1, 2, 3, blah, blah, blah. And so each time what we were able to do is to say, okay, above each we have our psi random variable. So this is functions. For each n, I have a function here. It will be zeta n. And then what I can do is for different omega, which are in capital omega, I just take the value psi n of omega, psi 1 of omega, or zeta 1 of omega, zeta 2 of omega, blah, blah, blah. And this is a sequence of 0, 1. And this I can read as being a sequence of integers, depending simply of omega. This will be my sequence A omega, or more precisely, it will be the indicator sequence of something which is 1 omega. So this is the random set A omega. Okay, I don't know if we went much further than that, possibly not. Yes, and so then I say the following, that Kn of omega is 1. So Kn of omega is 1 if it is in the set AI, so it is just this, okay. Good. Well, why did I put Kn of omega, not simply zeta n of omega? I didn't use the word zeta last time. I used K.
But the zeta is the random variable. When you define Kn omega just to be 1, if n belongs to a set.
Yeah, okay. But it is the same thing as in some ways zeta n.
Yes, right.
Well, okay. So maybe there's no point to add this Kn of omega. Okay. So now we were saying that, okay, well, this was independent. We know how it is. Good. And we stopped here.
You stop.
Good. Okay. So now what we do is the counting function of A omega. Counting function of A omega. There will be much in common with what I was saying this morning, but maybe it's not that bad to repeat, and in any case to say for those who were not here. Counting function of A of omega, what you look at is to say, let us say, this depends on omega, and for n, a given number, this is just the cardinality of the set A omega of the elements which are in the intervals 1n. This is usually the way you do the cardinality of a set, and this is a random function. And this random function, an of omega, A omega n, is the sum of the zeta n of omega, n up to n. Okay? So you can see in some way A of n, capital A of n, as being some random variable for each omega. You look at your set A omega, you do the sum, blah, 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 and it is just the sum of the random variables. Some way you introduce this is a random variable. A of n is the random variable. Summation n up to n of zeta n. Okay? So now you have something which will be about the number of the random variable. So if you can know what is the expectation of A of n. This is quite easy to get. Expectation of A of n is simply, since it is linear, it is the sum of the expectation of the zeta n. And this zeta n, for expectations in the Bernoulli random variable, the probability that it is 1 is the Pn. And so this is equal to P1 plus P2 plus Pn. Okay? So you have a good understanding. This is what you have. And now you see the point is that what we are saying is that to each omega, I have something here which will be zeta 1, here zeta 1 plus zeta 2, here is zeta 1 plus zeta 2 plus zeta n. This makes sense. And what you will get at this level, it's something of omega, let us say. So to omega, you associate also this, omega, blah, 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 and this is the counting function. This is the counting function of omega. Okay, maybe no, not capital N. This is the counting function of your random variable omega. And what we are saying is that we have some understanding of what is the mean value. Then you have something which is just to take the mean value, the expectation of an, of an, a of n, of a, let us say, and this you have it. This is the expectation. You go here, you take the expectation of psi 1, you take the expectation of psi 1 plus psi 2, zeta 1 plus zeta 2, blah, blah, blah. And this is the expectation you have. Good. But this is not what we are interested in some way. It's good. It's, for example, if you want to have something which is like a square, you would expect that the counting function should be something like square root of n. This would be a good hint. But indeed, what you are interested in is more to take one single omega and to look at what is this function. You would like to have this function to be, maybe not always, of course, you may have always some bad situation, but you know that when you are tossing a coin or throwing a die several times, there should be something which should more or less well average. And you would like to be able to say that this sequence has a behavior which is about the same one for everybody. So on this direction, this is easy. This is what we have done. We know what is this expectation. But what we would like to have is, we are interested, indeed not in this, interested in the following, that what can you say of, when you look at this sequence, a omega of n, and you would like this sequence for almost all omega. What we expect is that this sequence is close to the expectation of A of n. Which is a different problem. Okay? So it's not too difficult. Essentially, what you need for having something like that is there's some nice, it's not too difficult, but I don't want to give in some way probability proofs. But there is a nice result, which is the position. By the way, Shanta, you asked about getting some references for that. I think if you want, if you really don't know much about, you are more number theorist and you don't know much about probability, I think that a good point is to go to Halberstam and Roth sequences.
What's that? Halberstam and
I write it. Because then I'm going to forget. So Halberstam and Roth. It is not recent book. It is 50 years old, but it's quite interesting. Sequences. So volume 1, no volume 2. And there is a chapter on probabilistic number theory, and they prove exactly what they need for that. So it's maybe not the best way, the best place to find it, but at least you find almost everything besides one thing I am going to tell you, which didn't exist at that time, which is used for number theory. I don't know any other, in some way, simple explanation of what is additive number theory with probabilistic methods. I should have, well, okay, I made a mistake, but good. So here you can find whatever you wish. And by the way, since we are talking about references for the what is called usual probabilistic number theory, that is to say the study of arithmetic functions, then definitely you go to the book by Gerald Tenenbaum. You have it here in MSc, and definitely Halberstam and Roth should be here too. Okay. So I think it is an introduction to analytic and probabilistic number theory.
We have only the English version.
Sorry?
We have only the English version.
Yeah, you have the English version. It is what I give the title in English. Yeah. Okay. So now what we have here, the probability business will tell us that we don't need much to be able to ensure something like that. This is what we're interested in, and it's not difficult. We'll give one example to see how it goes. So it goes in the following way. We take xn, be a sequence of independent real random variable which are square integrable, and such that, so of course you see in our case we are dealing with Bernoulli random variables, so there is no problem about this. I give it in general, it's not much easier to do it in our special case. So first thing is that we are asking that the expectation of xn is positive. So in our case it's fine because expectation of xn, we're going to apply it when we have little pn and we assume that little pn is positive. Okay? So this is fine. The second thing is that what we expect is that what we assume that the expectation of x1 plus xn is tending to infinity when n is tending to infinity. But of course, if we want to have something which is more or less an infinite sequence, it's better to have that this expectation is infinite. Go to infinity with n. Otherwise, we have more or less something which should be a finite sequence. So definitely the Pn we are going to use, this means that the series of the Pn is divergent. Okay, we'll see what it is. So, and then something which is, again for us it will not be too difficult to show, is the following, that the sum when n is from 1 to infinity of v of xn. Okay, so for us it will be something which is in any case at most 1, but in some cases it may tend to 0, so we have to keep that. Expectation of x1 plus xn square, this series is convergent. Okay, so we gave one example, even two with the prime numbers this morning. Let me give another one. So, okay, example. We're interested in getting a model for squares. Sorry? Yeah, if you have that, then. Okay, we're just putting the hypothesis. Then, if you have all these conditions, then you're happy because you have what you expect. That is to say that x1 plus xn tends almost surely, when n to infinity, is equal almost surely to 1 plus little o of 1 times the expectation of x1 plus blah 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 plus xn. What does that mean, something like that? I have two functions. So what I am saying is that this is something which is true for any omega, except a set of omega of measure 0. So this means the following. If needed, I say it again. This means that if you look at the set of all the omega such that x1 plus blah 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 plus xn of omega is equal to 1 plus little o of 1 of this expectation, 1 xn plus xn. This set has probability 1. When you look at this horizontally, when you look at your sequence of the value of n, the counting function almost always is asymptotic to the expectation. This is the right thing we want to see. Okay? And the condition is not very complicated. Essentially, this will be something, the variance will be something like Pn. It is Pn times 1 minus Pn. So it is essentially Pn, and this will be P1 plus P2 plus Pn square. Okay, so you want the Pn divided by the square of the sum of the Pn to be a convergent series. So usually it's not too difficult to check. So let us give, we go to this example now. Example, you want to have something like squares. So what you would like to have is something which tell you that the sum of the expectation here is something like square root of n. Okay, so you have to find out, let us say, pseudo squares. You want to find a nice sequence a regular sequence Pn such that P1 plus blah 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 plus Pn is essentially something like square root of n. So you have some idea what you want to do. If you take some nice function, it is to take something like the derivative of this function because you are integrating when doing the sum. So a good choice, a natural choice, is to say that Pn is equal to 1 over 2 square root of n. Okay, if you have Pn which is 1 over 2 square root of n, then you have that. In some way you are happy, and you have to check that it is okay. So first, that it is positive. Yes, okay, they are all positive. This is not a problem. That the sum is tending to infinity. Of course, we did it on purpose that it is square root of n. So the only thing we have to check is that this series is convergent. Okay? Now the point is that what is Pn, what is the variance of Pn? So what we have to check, conditions 3 is given by the following. We know that V of zeta n is Pn 1 minus Pn, Bernoulli random variable. But we know that essentially, as regard the summation or something like that, up to a constant, this is exactly Pn. I don't lose when saying that this is Pn. Variance of a Bernoulli random variable is P1 minus P. Okay? The expectation square minus the square of the expectation. Okay? So you have this expectation of the square, but since it is with value of 1, the expectation of the square is the expectation itself. It is Pn minus the expectation square, and you get it. And now what is this series? So you have to look at your series, and so it will be 1 over Pn, 1 over 2 square root of n, so that the series 3. Okay? So to prove 3, you have this series over n, and then you have x1 plus xn, but you have done exactly on purpose to get square root of n. So when you square it, you have n, and of course this is convergent, and you are happy. Okay? So you're in a good condition, and you know that for almost all omega, if you do it that way, for almost all omega, the counting function will be up to n will be n, square root of n. So it looks like squares. Okay? So, okay, I want to go now to something which would be the sum of two elements. So it is, I don't know, well, okay, next thing. Sums of two elements. For example, I want to have some idea what is sum of two squares, or two pseudo squares, what it looks like. Okay, so what is Rn? What I will introduce as Rn here is the number of A inside my sequence A. So all that depends on omega. It is random variable for each omega. I have a sequence A omega, and so I have some number of representation. And the one I'm going to take is the one which are A is strictly less than n over 2, and of course n minus A belongs to A. You know, you have several possibilities for taking the counting function. One of the possibilities is to take all the elements which are distinct, sort of restrictive. This is what I'm doing. Maybe I'm losing in this. Well, if you have two different elements, counting just the smallest and then the largest, or both of them, you just introduce a factor 2. What may be a point is that an element n will be just exactly 2 times an element in my sequence A. Okay? This usually will give you another number of representation, but for us, you'll see it will be easier, and usually there is not a big difference between both of them. So it will be easier to consider this number of representation because, well, you'll see how it goes. So I want to say something about this random variable. Okay? So we consider the random variable which is essentially the number of ways up to a factor of 2 to represent an integer as the sum of two distinct elements of A. Good. So now I have squares, and I want to know what is the number of representation like that, squares or not. I can do that for a general sequence, and then I will use it for this special one. But let us look at what it is. So what I am saying is that if you wish, you can write it like that. Rn of W, if you want to go back to W, this will be, each time you are counting, you ask that this element is in A, so you are counting for all the element, j, between n over 2 and 1. I asked this element j to be in A, that is to say that I take zeta j of, of omega. So this will be 1 to say that my first summand is in that. This is the A. Okay, it is up to n over 2, this is fine. But now I have to say also that the other one is there. So this will be zeta of n minus j of omega. Okay, if one of these are the value only 0 and 1. It takes the value 0 except in the case when psi j of omega is equal to 1, that is to say j is in my sequence A omega, and this one is also in the sequence j omega. Okay? So this is quite nice because I know a few things here. What is interesting is that not only among those two elements psi j and psi n minus j are independent, but even in this sum all the summons are independent. Because if I take for two different j, if the j are different, the n minus j are different, and the n minus j cannot be the j because I'm restricting to n over 2. This is why I don't want to go up to n. I'm losing a tiny bit, but essentially all those are random variables, and all those random variables are independent. Okay? So not only psi j and psi n minus j are independent, but all the psi j, psi n minus j for j between 1 and n over 2, all these random variables are independent. Good. So can I say something about this random variable? Okay, let us write it as a proposition and then we'll see why it works like that. So, okay, let us assume as usual, my set of Pn, n at least 1, is a sequence of real numbers in 0, 1. Okay, we want to have it, let us say, which is decreasing, non-increasing, at least from some point onward. I'm thinking of this sequence, you see, for example, and I am assuming that and there exists a lambda such that positive, such that the sum when 1 is between j and n over 2 of pj n minus 1 is tending to lambda. So if you think of what I am doing, I'm saying something that the expectation here is something which is more or less constant. Why does it make sense? Well, it makes sense. This is just now, you see here what we are doing is to do the following. So maybe I go on with the statement and then I tell you what happened. Then for any integer d, positive integer d, non-negative integer d, one has that the limit when n tends to infinity of the probability that I will call that I don't know why I defined it Rn before, probability that Rn is defined there, okay, that Rn is equal to d. This gives a Poisson law. This is lambda to the d divided by d factorial e to the minus lambda. Okay, so let us try to understand what it means and how we can prove that. So, okay, there are two things. One thing is to apply it, how we can apply it in our case, and another thing is to know how we can prove it. Okay, we'll give the proof of that. Okay, so so this is that for the statement of the proposition. So okay, now you have some little exercise that if Pn is equal to 1 over 2 square root of n, this for squares, we are interested. You see, what can you say about the summation when when j is between n and n over 2, or something which is 1 over 2 to the square root of j times 2, so there will be a 4, something which will be Pn minus j, which is square root of jn minus j. Okay? So this is in some way a mess, but this is only calculus. You don't have to work too much on that. Now you can figure out what it is. That essentially what will happen is that something, what you have here is what? Oh. You may approximate that by some integral. And so you get something which is some beta function or something of the kind. Okay? And so essentially, this will be the case that this turns out when n is large, this will be something like a constant. So, okay, this tends to lambda when n tends to infinity. I mean, this has nothing to do neither with, as you can see, neither with probability nor with number theory. This is just calculus. Compare with an integral. Okay? Good. So this is fine, we can apply that. Now let us prove the proposition. By the way, this will be one of the part in all this question about probabilistic number theory, that you will have a large part which is essentially calculus. It tends to a limit.
Because, so that is bigger than 1 summation, is bigger than 1 over n. Okay, that's fine. S term is bigger than 1 over n.
Yeah, this is why it is a mess. But
Yeah, so if it term is bigger than 1 over n, so this is like. Just replace this integral, yeah. Okay, just replace the integral.
you are just integrating something which is integral of 1 divided by square root of x 1 minus x. You see? So it's fine because you have a square root, and the square root at the edges is something which will converge. So you don't have problem of convergence. You see, you put a 1 over n, you put something which will be a 1 over n, and then you have something which is j over n, and something which is 1 minus j over n, and then you see that what you have is a Riemann sum. Okay, so it is a Riemann sum. It's not, the function is not, well, may tend to infinity at the edges, but you get something which is an arc sine or something like that. And so you will get something which is an average number of representation where you have a pi which occurs into the business, and this is normal because you are counting points inside the circle. Okay? But, so I don't want to do it precisely, but it is something like pi square over 4 or something of the kind. Okay? Pi. Okay, now proof not of this, proof of this, which is more interesting for us. Okay. So what we want to say is, what is the limit law of this random variable? We know here what is this random variable, how it is done. So what we want to try to do is to say, okay, if we want the limit of a random variable, maybe what we call the law of a random variable, the law of Rn, what we can do is to take the characteristic function, because characteristic function and the law is just the same. So what we are going to do is to write out what is the characteristic function of that. Good, let us do it. I know what is Rn, and I want to see what is the characteristic function of Rn. So let psi n be the characteristic function of Rn. Okay? So what you are telling is the following. You are saying that phi of n, phi of Rn, phi n of t will be the Fourier transform of this sum. Okay? So it is essentially something which will be the expectation of the this which is just the IT. How can I say? So first of all, let us write what is the Fourier transform of this. Okay? So now, first of all, let us see what is the Fourier transform, the phi associated to the psi j, psi n minus j. Now, we know that those random variables are independent. So we know exactly with which probability it takes the value 1. It takes only two values, the value 1 and the value 0. Okay? So it takes the value 1 with the probability which is pj pn minus j. Okay? So you will get something which is pj pn minus j times something which is simply e to the it times 1. Okay? Plus, and then it takes the value 0 with the probability 1 minus pj pn minus j of e to the I t times 0. So e times 1. Okay, you are just using the fact that this is a combination of two Dirac functions, Dirac at 0 with the weight 1 minus pj pn minus j, and this. Okay? Good. Now what we are doing is we are looking at the sum of those random variables. But what is interesting is that this sum, these random variables are independent. So we said this morning, maybe I don't go too far, but you can think of that if you have nice function or any random variables, if x and y are independent, then the expectation of the product is the product of the expectation. Okay? And since the phi function, the Fourier transform is just the expectation of the random variable e to the I x, then you know now what is psi of n. I don't need that any longer. I know what is phi of Rn, and this is very nice because now it is the product of all this business. So it is the product from j between 1 and n over 2 of something which will be, well, forget about the e to the it 0. So this will be 1 minus pj pn minus j plus pj pn minus j e to the it. Okay, so you can see it. You see that pj pn minus j will be something which is small in any case. It is small because at least one of them is at least n over 2. The other one are bounded, and you know that pn is 1 over 2 square root of n. Okay, so this term is a small term. This term is a small term, so I would rather like to write it like that, j up to n over 2 of something which is 1 minus pj pn minus j times something which is 1 minus e to the it. Okay? And this is small. This is little o of 1. You have always one which is large. Okay? So the product of something which is 1 plus little o of 1 will be the same thing as the expectation, the sum of the expectation of the sum of the little thing. Yes, sure. This is what I am doing now. What I am saying is that I have a product of things which are 1 plus little o 1. Okay, you may think that this is in complex numbers, but in any case, we are very close to 1. Okay, you have elements which are very close to 1. So you can take the complex logarithm, which just extend. You see, you can always have a nice logarithm, which is around 1. Just say, oh, I am not going to cross that, I will may into difficulty, but otherwise you have a nice expression for the log. You can even expand it as a series.
You're saying that sum of the logarithm is converged between this product convergence. So you can find out.
Yeah, it's just the fact that the convergence of the product of what you get is the same thing. Okay, so you may. If you don't like it, then you go to generating function, and then you are happy because the value are just integral. But if you don't want to go to generating function, and we are using also only this, then you can say that this is something which will be essentially the same thing as the exponent of the log, and so it will be something which is what? Which is the exponential. What I'm saying is that I take the log, and so I take the exponential of the log, and the log will give me a sum. So, and the sum, and the log of the business will be just 1 minus that plus little of 1. So we'll get something which is exponential of minus the summation of the pj, pn minus j, and then you have something which will be 1 minus e to the it, and then you will have a little o of 1 in your business, and you are happy. Okay? But what we were saying is that this sum tends to a limit, which is the case for our pseudo square. Okay, we are saying that this sum is tending to a limit. So if this sum is tending to a limit, this will be, when n tends to infinity, this will be converging to something which will be exponential of minus lambda 1 minus e to the it. With this plus little of 1, and it converges to that. So for any t, simple convergence, for any t, when n tends to infinity, this will, the n is here. Okay, this is j up to n over 2. This will converge to this. Now, you remember what was Levy telling you? Levy is telling you that if you converge towards something which is, and by the way, we know if it is continuous at 0, you are happy, this is the case, but even if you know that this is the characteristic function of a random variable, then you have convergence in law toward this random variable. So you just have to know, what is this? This is the Fourier transform of what? This is the characteristic function of what? And you remember we did that, at least for those who were here this morning, this is not complicated. Take something which is just the Poisson law, and you see the Poisson law, you have something like that. And so you understand that if you multiply by something which is something like a to the it, you exactly get something which is this minus lambda 1 minus it, and you are summing all this element with the lambda d of d factorial, and you just get something which is this exponential. Okay, the exponential of minus lambda, you have it, and then you are just summing elements which are powers. So this is the Fourier transform, the characteristic function of the Poisson law with parameter lambda. Okay? So this is done now. You have this limit, you have converging in law because of Levy theorem. The most easiest part in some way in Levy, which is telling you if you converge towards something which you already know to be the Fourier transform, the characteristic function of a random variable, then you have convergence in law. Okay?
So there is a uniqueness property of that.
Yes, just the uniqueness. You don't need the complicated thing which says if it converges with a function which is continuous at 0, then necessarily it has to be something like that. No, you simply say I have a sequence of random variables such that the Fourier transform converges to the Fourier transform of a random variable, then they converge in law. Okay, it's not the full force of Levy we are using. Good. So we have this. This starts to be interesting, except it's not exactly what we want. What we want is something which is a bit different. Again, look at where we are. I think this is the most important in some way to know where we are and to know that there is some job if you want to go a bit further. What is the job? The job is the following. What we are saying is the following, that I am looking above the point 1, 2, blah, 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 n. I have something which is my random variable now, which is called Rn. Okay? And I know that what is Rn here above 2. I know what is Rn above n. I know what is my random variable. And what I am saying simply is that what I know is the expectation of Rn. So, okay, the expectation of Rn is something, or even what is the different values I get for Rn, but it is at this level that I know not only the expectation but the values. So you get the d is equal to 0, d is equal to 1, and so on. And what I am telling is that I know here what is the number of elements for which I get a 0. It is something which is 0 will be e to the minus lambda. The weight here is e to the minus lambda. More or less true, I mean, more and more true when n is large enough. So this will be around here. I will say, okay, take the value 0. The number of omega for which you take the value 0, it's about e to the minus lambda. 1 plus little 1. Yeah, but this is not what we would like to have. Again, what we would like to have, this is the easy part. This is why we prove it. This is the easy part, but what we are really interested in is to know, now I take some omega, I fix some n, some d, and I look at some omega. Now I want to know what is this sequence. It is more the Rn of omega for a given omega. What is this sequence? Is it true that it behaves? How many times does it take the value 1? The value 0? Is it true that you get the value 0 with a density which is e to the minus lambda? Is it true that you get... Now what I am counting here is something completely different. Okay? So this is nice proposition, but our real interest is the following. I don't need that any longer. Would be the following result. It is to say, okay, what I'm looking at is let D, I'm always in the same context. Same context as in the proposition, same hypothesis and in the proposition. Assuming all that. What I would like to say is something different, is I take some omega and I take some D positive. Then what I would like to say is what I can say about, for given omega, what can I say of the number of n up to capital N for which I get the value D. So for any D, what I want to see is the following. What can I say about the set of omega for which, well, what do I want to do is to say the following. I'm looking at 1 over n, and then I want to say the cardinality of n up to capital N for which Rn of omega is equal to D. What can I say about the density of this sequence? That this sequence has a given density. Of course, you would expect that it is again a Poisson law, because on average it's true. So if it has something natural, it has to be this, but it doesn't mean at all that this exists. Okay? So what we would like to say is that the set of omega for which this is equal, is tending to e to the minus lambda, lambda to the d divided by d factorial. I'd like to say that this probability is equal to 1. It is almost sure that the distribution function, when omega is given, then the number of those for which I have the d, and it's completely different from what I was doing. And again, you see, the other one was something which was just in law, and convergence in law is not that interesting. This is convergence almost sure. This is much more difficult. Okay? So this is the thing. Now you may say, well, okay, here is for all d, I have this probability. Can I put also the d inside? This is easy, because you are taking the intersection of, so it is countable intersection of elements which have measure 1. And by the sigma additivity, countable intersection of elements with measure 1 as measure 1 also. So you can put that into this. This is not a problem. It is okay. If you know how to do that, you can put the d inside. So essentially, for almost all omega, when you look at the values you get something like that. One corollary is easy. So I don't prove it, but just that you understand that it is completely different and that it is what we are interested in. And this is real probability problem now. You see, it has nothing to do with, essentially there will be some calculus behind, but it has nothing to do with additive number theory any longer. We're working in a model, and in our model is definitely something which is pure probability. Our imagination is to say, oh, this would be of interest for us, because it is, we can see it as a number of representations, so it makes some sense. But once you have defined what is the random variable which corresponds to that, you are purely in probability business. Of course, corollary is at least what can you say about the number which has a sum of 2 pseudo squared, that is to say for which this number of representation is non-zero. Well, such that 1 over n, the cardinality of the n up to capital N for which R of n is different from 0, that this tends to what? 1 minus e to the minus lambda, this is equal to 1. But simply, from here you know when it is equal to 0. Don't add to get that. Do not make addition of all those which are d which is larger than 1, because then you may get into, you need some uniformity and you are in a mess.
For 0 it is power minus lambda, and hence
Yeah, so for 0 you simply get e to the minus lambda, and so for the other one it is the complementary set. Okay? Don't start to, of course if you sum up it will work, but if you want to get the proof you need something, some uniformity. Don't go into that. Yeah, this is easy corollary too. Okay? Okay, so now we are going to see what happens if you want. So what we are saying is that when we have a sum of two squares, our probabilistic model tells us that there is a positive density for sum of two squares, usually. And this is not a good model for real life. I was, I think, mentioning that in the introductory lecture. Okay? This is not real life. So what happens? Well, you can modify this model saying, well, but the distribution in arithmetic progression is not that great. So you can modify it and say, let us have something which looks like more or less like squares in arithmetic progression, and then you will find that this will be 0. Somewhere you will have a lambda which will depend on the number of primes you are taking, and this lambda will simply tend to 0, and you will get something which is a 0 density. Good. This is fine. What about some, but we are not at the end of the business. Because you see, in any case, what was really interesting is that in R of n, we were only adding independent random variables. Okay? What about sum of 3 cubes? I mean, all that was introduced by Erdős and Rényi in a 1960 paper in Acta Arithmetica, and even the proof of this was not correct. Hmm?
what was the proof of this?
What else?
What you said proof of this was?
This was what Erdős and Rényi wanted to prove in 1960, but their proof is not complete. The proof is complete in Halberstam and Roth for 2 elements, and it's not given for 3 elements. It's just something like 3 cubes. What is the difficulty with sum of 3 cubes? That you will have a number of representation, which will be R3 of n, will be something like that. It will be a summation of elements which are psi n1, psi h1, psi h2, psi h3, for which h1 plus h2 plus h3 is equal to n.
So you mean that by any means omega? Or
Sorry?
so by any mean that omega?
What is the question? You are talking about squares or you are talking about cubes?
Here you use the symbol Rn of omega, right? So you are using R3 of n, that means
Ah, okay. Yeah, I understand what you mean. R3 of n. Sum of 3 cubes. So let us say, okay, let me go back to the beginning. Pn is something which will be, you want to have cubes, so you are going to say this is 1 over 3 times n to the 2/3. Okay? So if you are doing that, and if you are summing that up to n, you see that everything is fine and you have convergence. The number of elements will be essentially, up to n will be n to 1 cube, 1 over 3. So those are nice elements for cubes. Okay? And you do the same thing, and so you introduce now this random variable zeta n, blah, blah, blah. Now you want to know how many times you can represent an element at sum of 3 cubes. And this is for what you expect to have something which will be a Poisson, again a Poisson distribution. So if you are interested in sum of 3 cubes, this is a definition of this. Rn is the sum of zeta h1, zeta h2, zeta h3, and this is when h1 plus h2 plus h3 is equal to n. Okay? Now you can say that one is small and then the sum of the two others has to be large. You can do something like that. This is not a problem. That we were doing for the squares, it's okay. But what is a real problem is that when you are going to take two different elements in this sum, they need not be independent. You see, the point is that when you are saying that j plus n minus j, of course we are talking those two terms, is equal to j prime plus n minus j prime, then of course this means that j is either j prime or n minus j prime. And if you put something on the sides, you are sure that they are the same. Now when you are saying something like that, well, they need not be exactly the same. You may have something which is if you have h1 prime plus h2 prime plus h3 prime, it's equal to h1 plus h2 plus h3. It doesn't mean at all that it is essentially the same. You can always order them if you wish to say that I take h1 less than h2 less than h3, and even letting aside the representation for which you have two elements which are in common. Even if you do this cleaning, when you have something like that, even with that, you may have, of course, h1 prime is equal to h1, but then those two are different. This means the following, that you are now in a situation where those random variables, even if you put something like that, they are no longer independent. Well, possibly they are not too badly independent, but they may be, but then they need not be independent. Definitely there is a difficulty. And this is why, if you look in the Halberstam and Roth, nothing is done for the pseudo cubes, because this is a real difficulty. So this difficulty was solved by a student of Wirsing, Heinrich Gogel, in 75. It's not that known. This is why I write the name, and if you know it, you will go to MathSciNet and find the paper, because the paper is written in German. So it's not that well known. It deserves to be better known. This paper by Heinrich Gogel. So he turns out this difficulty by taking powers, moments. This is rather heavy machinery. Now we have a better tool, but this was introduced only in the early 80s. So you see in the chronological order, you see Halberstam, Erdős and Rényi, this was in 60. The book of Halberstam and Roth, this was in 65. Gogel was in 75. And then in 82, there was some nice tool which says, okay, there is a way to handle something. This is what I was starting to say this morning. We have a way to handle something when you have not exactly independence. Okay. So what is I want to say two things about this quasi-independence. One was introduced by Erdős and Rényi themselves, which is a nice one, not in this paper about pseudo powers, but they introduced something. So in some way what I want to say now is, I showed you simply what is the difficulty. The result will be the same. If you look at this, you will have something which will be a Poisson distribution, and everything is fine, I mean, as regards the result, but to prove it, you need some tools. So the tools, let us say two tools dealing with.
So what is the character in that case? So here you showed that the character lambda is nothing but the sum of ej, b, n minus j.
Yeah.
J varying from 1 to n minus n by 2 and tends to infinity, right?
Yeah, you get exactly the same thing with the different lambda, but for three pseudo
Now you
cubes.
have three probabilities there.
Yeah, if you have three pseudo cubes, it's the same thing. In some way, this is quite natural. If you have it is something which is well known. If you have done some probability, this is some exercise you have. If you have something which is on the mean, people are arriving at a place for getting some service, and they arrive as, on average, the same distance, the same time. Indeed, what you will observe is that the difference between the time they arrive is something which follows a Poisson law. So in some way, something which is, if you draw something on average which is constant, then the distribution will indeed be a Poisson distribution. So this is quite natural that if you expect that the average mean value is a constant, then what you see is something which is a Poisson distribution. There is nothing surprising in some way about that a Poisson distribution arrives. This is simply because we know that this is constant on average. We did everything so that we have something which is constant on average. Averaging is always easy to get. So dealing with non-independent, almost independent random variables. So just to that we understand what it is, how it goes, but so we were talking about Borel-Cantelli. Borel-Cantelli is very useful in this context. Essentially, when you want to say that something occurs almost never, while you say the sum of the probability of the events you are looking at is convergent. On the other hand, if you say the sum of the probability is divergent, it doesn't mean that almost always something will occur infinitely many times, but if you have some independence, you are happy. And the version of Borel-Cantelli in the non-independent case is the following, and you will understand what we mean by that. So, okay, I am in a probability space, and I have some Aj, family of Aj, which are events, and I assume that the summation j is equal to 1 to n of a probability of Aj is tending to infinity. Zn is this. Or if the probability, if this series converges, then there is no problem. This is the usual Cantelli business. You don't have to say anything. What is the other way around when it diverges? Then you want to say that something occurs infinitely many times. So, okay. So, if Aj are independent, then what you want to say is that plus some condition, and then the thing would be, then it implies then, so leaves some room in between. What I want to say that the probability of the intersection I is equal to 1 to infinity of the union j is equal to 1 to infinity, I to infinity of the Aj, this is equal to 1. So let us first understand there is something in between. This means the following, that if I am looking at some omega, what does it mean that I have an omega in this business? Omega in this business mean wherever I am, my omega will almost surely belong to the union of j is equal to I to infinity of the Aj. Well, it means that it belongs almost surely to infinitely many of the Aj. Okay? So this is in some way the threshold which tells you if this converges, then almost surely this set will have probability 0. So almost surely it occurs only finitely many times. And this is just using the fact that the probability of the union is at most the sum of the probability. And since you are truncating here, you just have the rest of the series, and this is tending to 0, and you are happy. This is the Cantelli business. Now, if you want to get that, you need something. For example, the classical Borel-Cantelli is telling you if the Aj are independent, then you have what you want. Okay? So the Erdős-Rényi condition is this, and this is very convenient, is limit inf of Zn minus 2 times the sum when A is between J and N of PAI intersection AJ minus PAI PAJ. You are asking that this lim inf is equal to 0. So just to understand what we are saying, of course, if the AI and AJ for I different from J are independent, then it means simply that this is 0. And so this condition is obviously satisfied if the AJ are independent. Understand that if you have not too many AJ which are independent, or if the probability of AI minus intersection AJ is close to the probability of the product, sufficiently close, then you have also the good condition. Okay, so this is, and this was introduced by Erdős and Rényi, and you see I was saying in the very beginning, you have some cases where number theoretic question may lead you to probabilistic problem. This is obviously a problem which is a pure problem in probability, which has been introduced because of the number theorists who were looking at some questions. We needed to have something like that. Essentially, it is to say here, well, this will not occur too often. So it's not far from being independent. Not far from being independent, you're happy. You may use theorems which are known when they are independent. So this is one of the tools. Yeah? Sorry? Lim inf, yes. It is enough to have a subsequence of n on which this tends to 0. If you have difficulty with the lim inf, forget about the lim inf, or you say there exists a sequence of n for which this tends to 0. Okay, you can in some way truncate wherever you wish, you need not go that far. So it is enough to have that. Okay, and maybe the tool which makes life very easy that was not available at the time of Randolph and Roth is Janssen inequality. And again, you will see some flavor of something which is okay. So, let us say this is the other tool, which is called this time Janssen's correlation inequality. Okay, you consider again, as usual, a probability space, and you have a family of events, AK. Let us say they are finite, little k between 1 and capital K. So those are events with probability of the AK which belongs to 0, 1. In some way, if the probability 0 is 1, this is not really interesting. You can suppress them easily. So it's not a big restriction, but if you want to write something which makes sense, you have to assume that, but it's not a big restriction. Now, we consider a family AI, a family of events. Each of which is an intersection of elements of my family EK. Okay, this is very nice because you see what we are doing each time. Consider that our AK are the fact that zeta k is equal to 0 or is equal to 1. We're essentially dealing with the fact that we are considering something where you have a 1 or a 0. They are independent, and we are looking at something which will be the sum of the zeta is 1, and so it will be 1 minus the business of the other one. So this is fine. So we are in this family. And then it tells you the following, that only with that you have, first of all, the lower bound was known before Janssen. Technically it is called FKJ inequality. And it tells you the following, that if you take the probability of the intersection of the complementary part of the AI, which is the type of thing we are looking for, this will be larger than the product of the probability of the AI. So this is fine. As regards the lower bound, if you are in this context, don't worry whether they are really independent or not. It will behave as if it was independent. Okay? And now the upper bound tells you, okay, what you have is the following. It will be the product over the I of the probability of the AI C. Well, this would be fine. This is if everything is independent. And there is some factor in front of that, times something. Times something which is exponential of 2 times, well, maybe there is some condition to say here that I assume that probability of EI is at most 1/2. But if you replace the 1/2 by something else, you can change the constant here. Okay. It was useful in our case to change the constant here. Well, I will tell you later why it was important to change the constant here. So I is different from J. And what we say, we are simply interested in summing when AI and AJ are not independent. That is to say that if everything is independent, I am happy, there is nothing in this sum. And so exponential of 0 is 1, and you are in the right case, of course. And then you will have something which will tell you that this is the probability of the AI intersection AJ. Okay. So now this tool is usually very good. In some cases, it's not that good because it may give you some error term which is of the same order of magnitude as this one. So you may change the thing by something which is just a constant and you are not very happy. So for what Marius Iosifescu and myself were doing, which was to try to look at the number of representation, for example, as sum of 3 pseudo-squares. So pseudo-squares is fine, you know how they are, but you are looking at representation at 3. So of course you would expect that the number of representations tend to 0 rather quickly. You would expect that everybody can be represented. Already with 2 you have something with positive density. Take a third one, it should be going rather quickly to 0, which is true. But as we got the probability that Rn is equal to 0, we have 2 terms of the same order of magnitude, one coming from if it were independent, and one coming from that. And so we wanted this to be, although of the same order of magnitude, to be something a bit smaller, otherwise we're in a distress. And to get something a bit smaller, we were playing with the factor here. So you can here change this, let this go to 1. We are not, it was not a big problem for us, and then you get something which will be smaller here. Or no, ask him to be closer to 0, and then you have something which is closer to 1. Okay, so again, you see this is the case. Okay, if you have not too many elements which are independent, now if they are independent, and you can say something about this probability, even if they are not independent, their intersection is very small, you are happy. Again, when you want to use that in real life, once you have written that, everything is just calculus. It's a mess, but it's calculus. And so this is why it's not that that funny to give that. So okay, this is now the case would be really can we do something better than that in some of the cases where it is important, where we would definitely have something. I mean, we have the impression that in some cases this gives us a too large term, and possibly this is just an artifact of the method. The real life should be better. So is it possible, for example, to use moment methods like Gogol is doing, the type of things I'm looking at on this part? Okay, I think I can close here. By the way, it is almost 5. And thank you very much for your attention. And if you have some more questions, please.
Can I take a couple of minutes?
Sorry?
Can I take a couple of minutes?
Can you?
Take a couple of minutes?
Oh, yes, sure. Even I tell you, you will be recorded forever. No, okay, so thank you very much.